All right, guys, so we're going to go ahead and talk about Newton's laws today. Yesterday you watched a brain pop video on who Isaac Newton was, and today you should watch a brain pop video on Newton's 3 laws of motion. Let's go ahead and get started and talk about these notes so that you understand them a little better. Newton's first law of motion states that if the net force is 0, an object will stay still or will continue to move at a constant speed unless acted upon by an outside force. What this basically means is if you've ever been asked by your parents, hey, where is this? Let's say keys. Hey, where'd you leave my keys? Oh, I left them on the kitchen counter. And then your parent goes and looks for it and says, well, they're not here. They couldn't have possibly gotten up and moved away. What your parent is actually stating is the Newton's first law of motion, and they are absolutely right. Those keys will not move. They will stay still because the net force is 0 unless acted upon by an outside force, like someone came and actually moved the keys. The example I put here is a coffee mug sitting on a table. In this example, the net force is 0, meaning that the forces are balanced. So this coffee cup will stay here forever and ever and ever unless it is acted upon by an outside force, meaning someone comes along and moves the coffee cup. Okay? So the coffee cup will not move unless acted upon by an outside force. Pretty basic, meaning that things don't just move on their own. They will stay standing still forever and ever. Now, this whole idea of a constant speed, this is not anything that we see here on Earth, because on Earth we have friction. And as you know, friction opposes movement. So if you were to kick something, it will move, but eventually will come to a slow stop, like if you kick a ball, because there's friction occurring in the ground. There's wind resistance. There's all kinds of different things that are reacting. The only time we see things move at a constant speed forever and ever and ever and ever would be in space. And this is like if you think of an asteroid or some kind of space rock floating along in space forever, it will continue to move at a constant speed unless something comes and bumps it off its course, and now it changes direction. So the only time we see this constant speed thing is only in space. Otherwise, we're talking about something sitting completely still unless acted upon by an outside force, meaning something came along and moved it. Okay? So Newton's second law now. Newton's second law deals with the fact that the acceleration or the speed of an object depends on the mass and the force acting on the object. This is very, very basic. Think of it this way. How fast something moves depends on how heavy it is and how much of a force you're applying onto it. So I put an example here of a person kicking a soccer ball. Now, most of you have had some kind of experience with this. If this person puts a lot of force into their kick, that soccer ball is going to move really, really fast, right? That means that the force, you increase the force, you're going to increase the acceleration, just like the notes say right here. Lots of force means lots of speed. That soccer ball is going to have an increase of speed, okay? Now, the other thing that affects speed is the mass. In other words, how heavy something is. So let's say we take this example and there was a way to make sure that this person kicked with the same amount of force every single time. Like let's say there was a way to measure it. We had some kind of, I don't know, some robotic leg that was able to kick the ball. And let's say they kicked the ball with the force of 20 newtons. So we have this leg coming in. It's going to kick this ball with the force of 20 newtons. And now this soccer ball is going to move. It's going to pick up speed. Let's give the speed, for the sake of argument, 20 miles per hour. Okay? Person comes, kicks the soccer ball, force of 20 newtons. The ball is going to move 20 miles per hour. I'm just making this example up. Now, what if we switch the soccer ball? If we switch the soccer ball for something that is not as heavy, so we're affecting the mass now. If we switch the soccer ball to, let's say, a beach ball, and we still kick it with the same amount of force, what's going to happen to its speed? Well, it's going to go up. It's going to move a lot faster than the soccer ball did because that beach ball has a lower mass, right? Since the beach ball weighs less, it's going to take off really fast. So let's say we kick this ball with a force of 20 newtons. It's a beach ball. Instead of going 20 miles per hour, now it's going to go maybe 60 miles per hour. Okay, so I'm making up the numbers but hopefully you understand my logic behind it as I say that the acceleration or the speed of an object is affected both by the force and the mass. And this is an equation that you want to make sure that you kind of remember. Now, obviously, if we want to get acceleration by its own, what you would have to do is you divide both sides by m. So it would be force divided by mass is equal to acceleration. Okay? Any of those two equations would be the same thing. And if you wanted to get the mass by itself, you'd do the same thing. You divide acceleration by both sides. The whole point of Newton's second law is that you take into account that all three of these things work together. How hard you push something, or pull it, or kick it, how heavy it is, and how fast it's going to move. Okay? All right, let's talk about the last law here, Newton's third law. Newton's third law of motion is probably my favorite one. This says that for every action, there is an equal and opposite reaction. So have you ever had anybody, or maybe like your parents, spank you, and they might say, like this example, this hurts me just as much as it hurts you. And you're thinking, yeah, right, no way. Well, actually, they're stating Newton's third law of motion. They are absolutely correct. For every action, there is an equal and opposite reaction. I usually have my students take their hand flat and slam it on the desk. And if you do that right now, go ahead and do that now. Take your hand and slam it on the desk. Okay? You should feel something as soon as your hand hits the desk, right? You feel it kind of slapping you back. And that's that every action has an equal and opposite reaction. So the example I drew here is, let's say a person decides to punch a wall, right? This person's really bright, very bright person decides to punch a wall. Well, the applied force with the same amount of strength that they hit the wall is going to kind of push it back on them, this equal and opposite reaction. And this is why oftentimes you see people who break their hands by hitting windows or walls, because guess what? There's an equal and opposite reaction. So if you hit the wall very lightly, it's not going to hurt as much. But if you apply a crazy amount of force, like really, really hard, guess what? It's going to bounce back just as hard. So it's going to hurt more. And you can do this really quick just by slamming your hand on the desk. If you just lightly tap it, that didn't hurt at all. If I take my hand and I slam it down with lots of force, that equal and opposite reaction is going to get stronger. It's going to hurt a lot more. All right, guys, so those are the 3 examples of Newton's laws and just an explanation of the notes. What you're going to have to do tomorrow is come up with a Flipgrid with your own examples. Do not use the examples that I gave you. You got to come up with your own stuff now, okay? So try to think of some examples in real life where you see Newton's laws in effect. Don't use mine, use your own. All right, guys, have a good afternoon, and we will talk soon.